Hi, this is Mark Brezinski again. This is lecture 3 in the OCT series, and it's lecture 2 on the physics. And today we're going to be covering lateral resolution. So there's a tendency to focus in on the axial resolution because the lateral resolution is the physics are very similar to microscopy. They actually are the same as microscopy. And so, but they're just as critical as the axial resolution, which is the resolution into the tissue or into the sample. The lateral resolution would be in a plane, a horizontal plane, whereas the axial resolution is penetrating into the tissue. And they roughly need to be the same, and they're dependent on different mechanisms. And the lateral resolution becomes really important when you're building catheters and endoscopes. I'm hoping this will be a short lecture uncharacteristically. So again, my name is Mark Brezinski, and I've gone over my background in previous slides, in previous presentations, so I'm not going to do that again. Again, this is not a pitch for my textbook, but chapters 1 through 4 cover this in greater extent. It's college level physics before we get to OCT in chapter 5. And the topic is covered to some degree in chapter 5. I don't remember the section off the top of my head. So if you find classical optics boring, so do I. But it's critical. I'd rather do quantum optics or fiber optics, but we need to go through it. So much focus is placed on, again, the axial resolution, and we discussed this in the previous lecture. The axial resolution is dependent on the bandwidth of the source, and we generally describe this for a Gaussian or bell-shaped beam with respect to the frequency distribution. And in terms of, you're going to hear the term full width half max. So full width half max is roughly the height halfway point of the peak where your intensity is at 1/2. And the reason we have to do that is a Gaussian spectrum is infinite in extent. So as you go down, it just spreads out and out. So we have to pick a point where we define the width of the spectrum or the resolution. And so the axial resolution is determined by the full width half max of the point spread function or the coherent length. You'll hear the terms of, and it's the ability to separate two peaks. So I want to make a point with this in the fact that, so if the axial, all we need to do is increase the bandwidth of the source to get more resolution, then great. We just broaden the bandwidth and broaden the bandwidth, and we're going to get higher resolutions. And it's not that simple, as so many things are in life. And I want to make a second point. This equation holds for both time domain and spectral domain OCT, because I constantly get the statement or the question, oh, spectral domain OCT or swept source OCT has a higher resolution than time domain OCT. And that's not true. It likely you're working with a system with better electronics, better performance, but the resolution, the principles in the resolution are identical. So with axial resolution, we're going to discuss at the end of this talk things that reduce the axial resolution, particularly dispersion. And we discussed in the previous talks, I'm not going to do it again here. We need a Gaussian spectrum, and this was covered with Fourier mathematics, and I'm not going to recover that again. But if the spectrum is not Gaussian, if you're losing wavelengths as you're traveling through the sample, or if dispersion is occurring, which I'll discuss later in the talk, then the axial resolution deteriorates. So it's not just purely dependent on the bandwidth of the source, or as we go back to the previous equation, the square of the median wavelength. Now the lateral resolution is essentially dependent on the lenses, but it needs to roughly match the axial resolution, or else having a high axial resolution is of no good. So the worst you can do is match 2 to 1. So have an axial resolution, lateral resolution that's twice that of the axial resolution. So an axial resolution of 10 with a lateral resolution of 20 is still reasonable. But after that, the images become very difficult to interpret. And the lateral resolution is determined on lenses, which is going to be determined on diffraction and refraction. And we're going to focus in on the topic of diffraction, which is ultimately going to limit our lateral resolution. So this is from my book, but it was modified from Heck's textbook of optics, which is referenced at the bottom of the slide. So light bends in response to an interface of two different refractive indices. And refractive indices, for the purposes of this talk, is the speed of light in the medium. So air, we can approximate, has a refractive indices of approximately 1, very similar to a vacuum, whereas water would have a refractive indices of around, let's say, 1.35. And so that will bend the light. And it's discussed in the book why this occurs, and I'm not going to go into detail here. But we can use that principle to focus light. So here you see that a lens isn't the same width all the way through, and you're able to focus the light to a point. And so that sounds great. We focus it to a point. So if our resolution is 5 and the axial direction is 5 microns, then let's just focus the light in the lateral directions to 5 microns. And there's a problem associated with that, as you see, and we're going to discuss this in some of the slides to follow. If you look at the black lines after light hits the lens, the outer light is directed at the focal point in the focal plane, and then it spreads out. And the tighter we focus that light, the more rapidly it falls off of focus from the focal plane. So if we focus to 1 micron, we're, let's say, 5 microns, then we've doubled at 5 microns from the focus. We've doubled to 10 microns our focal point. And I'll go into that in a moment, but it's not a collimated beam that stays the same width through. When you focus it down to that size, it's only going to be that focus, that spot size at the focus. So there's a basic principle. So when light passes through a given area, the principle is that every point behaves like a new source, and light mediates out of it in all directions, and the phase is going to vary from these different points down this slit. So what we're seeing is light waves hitting a barrier with a gap in it, and then we treat it, for a good approximation, is that each point represents a new source. So what this is going to result in is a diffraction pattern. So this, again, the image on the left is from my book, and the arrow was somewhat confusing, so I put a yellow square over it. When you're close to that slit opening, and that slit opening is the same principle as our area of focus. Um, the distribution resembles the Gaussian distribution at the focus. But as you get farther and farther away going, so the bottom would be close to the slit or the focal point. As you get farther away, you go, the diffraction pattern starts to distort the image. And so closer to the slit or the area of focus, um, that's known as near field diffraction, and farther away, that's known as far field diffraction. So you can see this from the image on the right in the far field, that we see that the light is broken up. So we're losing a lot of our intensity. And it's being spread out to side pixels. If you remember from the previous lecture, we need to plot each point that we're imaging with the OCT beam into a pixel. And it's essentially bleeding over into the next pixels. And this is shown here in somewhat of a rough drawing again from my book. So if we have a very large gap, or we're focused onto a very large area, let's say our focus is 50 microns, then the beam coming out of it is relatively collimated. But the tighter we make that, the more rapidly dispersion causes the beam to dilate out. So this becomes a very important principle in how we use OCT and our ability to get down to resolutions below 10 microns. So if I don't mention it, we're almost always talking about a Gaussian beam or a bell-shaped distribution of light. And so here we're talking about a bell-shaped distribution of intensity. So this slide demonstrates the point of focusing in. So if you look at the area where there's 0, we focus the light beam in to that area 0, and the confocal parameter, or half of that, the Rayleigh range, is the area over which that will double. So you can see here where it says across the top 2z0, that's the distance over which the area we're focusing power into doubles. So the light is spreading out, we're no longer focused. So the higher we try to focus in on a spot, the quicker we fall off focus away from the spot. So it may be starting to become apparent that if we focus into 1 micron in the spot within a tissue, 500 microns away from there, that's not going to be anywhere close to 1 micron focus. That's going to be in the hundreds of microns in the focus. The other point I want to make, when you look at a drawing like this, again, we're using a Gaussian beam. So we pick a cutoff point like the full width half max as to represent that spot size. So that spot size is roughly 86% of the intensity. And that drops to half the intensity at the confocal parameter and or the Rayleigh range. And this becomes really important when we get below 10 microns. So at 5 microns, our confocal parameter is 5 microns, which means that we've doubled. It's no longer 5 microns. It's a 10 micron beam. Even though your axial resolution may stay high, your lateral resolution has now deteriorated, and your intensity is cut in half after 5 microns. So it becomes very hard below 10 microns, and this slide shows the relationship, below 10 microns to get that lateral resolution to match. So this is a huge problem in catheter and endoscope design. And what we do is, this is where people use the term confocal OCT. What you do is you scan the focus. So as you're imaging within the tissue, you're moving the focus um, to different depths within the tissue. This is obviously much more complicated than having a fixed lens. And this is very difficult to implement in a catheter or endoscope. It's possible, but it's very difficult. And so when people, or it's very common for people to say, oh, we achieved this with confocal OCT. Yes, that's true, but actually implementing this in, say, a coronary artery or in the GI tract is going to be extremely difficult with confocal systems. So hopefully you understand now the principles of lateral resolution. I just want to touch on loss of axial resolution, and in this case, dispersion. The other way you get loss of axial resolution is if your beam is no longer Gaussian, and we explained that principle in the last um, presentation. And so if you're losing wavelengths because of absorption in the tissue, your beam is no longer going to be Gaussian, and then the Fourier transform, which is what's plotted in a given pixel, is no longer Gaussian. So you'll get peaks in the adjacent pixels. So your resolution will deteriorate. But what we're going to talk about here is dispersion. So not all wavelengths travel through medium at the same rate. So the top left shows a Gaussian beam, and if you remember from the first talk, we have an envelope and a carrier frequency. And OCT, we're generally focused in on the envelope. The carrier frequency is used with phase-based techniques. It also helps us with things like noise reduction. But so the envelope is on the carrier frequency. And so the top slide shows dispersion. So not all frequencies are moving the same through a medium, let's say lipid. And so you're going to get broadening of your Gaussian wave packet, and you're going to get a reduction in resolution. And the bottom is from one of our earlier papers, a 2004 paper, looking at the point spread function in lipid, water, and air. Now, this becomes important for resolving. So this is based on work we did in Physics Review A, this particular slide, but honestly, most groups have reproduced images like this who work in the OCT field. So I think this is a glass cover slip, so we have two reflections. And we define separating two reflections if we've got over 50% of the peaks are able to be discriminated. So as we go to B, as we widen our wave packet from dispersion, we now are getting overlap between the two peaks, but more than 50% of it is discriminated. So we still consider this to be resolvable. But as you see, as we in C, as we broaden even further with dispersion, the point spread function, we no longer can discriminate between these two peaks. And so we've lost our resolution. So dispersion is leads to a loss in resolution. And you can get dispersion from the medium. You can also get dispersion from the fibers. So why do we use single mode fibers? And this again is from my textbook. But if we use the multi-mode fibers coming in at different angles, and this is a classical description if you do work in quantum optics, This is sort of going to turn your stomach, but you can envision that light beams are able to come in at different angles, and they take different times to travel down the fiber, and this would be called a multimode fiber. And by the time it gets to the end, if you look at the left of the multimode fiber, we show a pulse, and when we look at the right, the pulse has been distorted because different light beams coming into the fiber are traveling at different rate, and it widens out the pulse. Now, if we use a single mode, then only one mode makes it through. So that's why we use this tiny 9 micron core in OCT. It's because if we use a larger core, the longer the fiber, the more deterioration we're going to get. So so what I've just talked about translates into a variety of issues. First, inside our catheter, we need a fiber with a roughly 8 to 9 micron core with roughly 128 micron catting around it. The fiber itself is 100 and let's say 130 microns with a core of roughly 10 microns. And then we need, in this particular case, we use fiber lenses, which are called grin lenses, which focus the beam. But again, if you were to go below 10 microns, you're going to have to adjust that focus. So it's no longer this simple design of a fiber that's being rotated by a speedometer cable, a grin lens, and then a prism which acts as a mirror and directs the light. We have to alter that lens, or the gap between, say, the lens, the fiber, and the prism, to alter the focus. So it becomes much more complicated. And then we've discussed the problems on the proximal end in the previous discussion. And then finally, this is an area that's somewhat unique to ophthalmology. There's an added issue of the lateral resolution being compromised by the pupil. That's an entirely different topic. I may take it in a separate lecture. If not, it's discussed in the ophthalmology literature. And then finally, these are just some of the NIH grants that I've received, but Jim Fujimoto has also received a considerable number of NIH grants to do OCT research, and we'd like to thank the NIH for funding, 25 years of OCT research. Thank you very much.